All right, AP Physics. This is the answer preview video for the test that you're going to have on Friday, April the 18th. So you should know how to do all of the problems on this particular review set. So let's go ahead and get started. The first is a basic ramp problem. All right, so you can see what you're given there. There's no friction involved and there's no initial velocity. So we'll draw a free body diagram, FBD. And the action force is the weight, the gravity, the force of gravity. And the one reaction force that we're showing here, there's no friction, so that's going to be the normal force, perpendicular to the surface of the ramp. Okay, now I'm going to come down here to draw the components. So components are going to go parallel to the surface and perpendicular to the surface. So if you want, you can just come down here and take that about that angle. It doesn't have to be perfect. And do that. And then perpendicular to it. Like that. Okay. This one's the normal force. And it equals 0. So we have, the friction force. This is the friction force, and that equals 0. This is the normal force, and this is the ramp force right here. Okay, so we can come up here and do the dashed lines as we've always done them. They're always exactly the same. We have an angle of 25. Okay, so there are the two components. So this one's going to be the normal force. This one is going to be the ramp force. Okay, so we have, this is the force. We want to know the acceleration. So force equals F equals ma. These two forces cancel out because the box is not moving in either of those directions, so they're equal and opposite. No friction force going back, so we're going to solve this to be A equals F over m. So that's the force right there. And the m is just simply, we're calling it m. We could call it 1 kilogram if you'd like. Okay. So we're going to plug in numbers. I'll write it up here. M equals 1 kilogram. Okay, so we come down here and the acceleration is, and the sine of 25 is just about 0.42. Okay, and of course that's all over 1 for the mass. Mass could have canceled. So acceleration equals 4.2 meters per second squared. All right. So how long will it take this block to slide to the bottom? It has that acceleration. And we know the initial velocity is 0, so we can use this formula. Okay, so we're first going to find the final velocity. So that's this one. Okay, so we multiply that out. VF squared equals 168. And if you take the square root of that, you get VF, the final velocity. And that's just about 13. We'll just call it 13 meters per second. All right, so now the time is going to simply be, if we want time, so there we have VF equals that. We know V0 is 0, so we can just kind of get rid of that. So what we have for time is time equals, divide both sides by A. Okay, A right there, VF right there, and we get 3.1 seconds for the time down the ramp. Now next it says, find VF using conservation of energy. Okay, so we know that the potential energy of the block, we're calling it a 1 kilogram block at the top, is equal to the kinetic energy at the bottom. So we can write that as, this is the way I'd actually like you to write it, is PE. Okay, so the PE plus KE at the top gives you the mechanical energy. That's going to equal to the mechanical energy at the bottom, PE plus KE. So at the top, it's mgh plus 0. There's no motion initially. And that's going to come over here, and that's going to equal PE at the bottom, which is going to be 0, because when it gets here, there's no height. So that's going to be 0 plus 1/2 m V final squared. Okay. Now first we need to know the height here. Okay, and it's just simple trigonometric. This is the opposite. This is the hypotenuse. You have a 25-degree angle. So sine 25, or opposite, which is the height, equals the hypotenuse times sine 25. Okay, and that's going to equal 8.4 meters. All right, so now we keep going. Okay, so from up here we have mgh equals 1/2 mv final squared. Okay, so we get the same answer using the conservation of energy method. Now I also asked you to show the work done by the Earth. So the work done by the Earth should be the change in energy. You could either pick potential energy, the change from its number, mgh, which we just said is 84, or the kinetic energy would be the same change from 0 to 84. Okay, so let's go ahead. So work equals force times distance. And the force is, come back to this side, the force is mg sine 25, so that's 4.2 newtons. Where did I write it? I actually didn't write it. I should write it here. Equals 4.2 newtons of force. That's 0.42 times 10 times 1. So we come over here. 4.2 times 20 meters is the distance. And that is going to give us 84 joules. It's the work done by the Earth on the box. And that is what we got. Okay, and that's what we got right here, 84 joules. So the potential energy went from 84 down to 0. That's the amount of work done. Or the kinetic energy went from 0 up to 84. You can use either one, and that is the amount of work done by the Earth. So that's that problem right there. Okay, this problem is identical to the last one, except it includes a friction force, and the coefficient of friction is 0.2. So the formula for friction force is coefficient of friction mu times normal force. Right there. Okay, so I've pretty much already set up everything the way it was on the last problem, except right now, right here, we're going to add the friction force equals mu times this normal force right here. Okay, and so now we can go down and figure out acceleration. Let's just figure out numerically what the force is going down the ramp and subtract the force of the friction. And that's going to give us the net force going down the ramp. That's simply the ultimate force that you finally end up with going down the ramp once you subtracted friction force. We call that F net. Okay, so it's 1 times 10 times 0.42. It's going to be 4.2 minus. Okay, so the friction force is going to be mu, which is 0.2. Times the mass times gravity is 1 times 10 again, and now that's the cosine of 25, which is 0.9. So let me write all that out. It's actually 0.91, so I'll write that right here. Okay, and when we multiply that out, okay, so when we multiply all this out, the coefficient of friction, m and g, 1 times 10, and the cosine of 0.25 is about 0.91. We get the friction force of 1.82 newtons. So we're going to bring that number up here and subtract it. About 1.8. That gives us 2.4 newtons pointing down. Okay, so that's the amount of force that's actually taking us down the ramp. Okay. So now we have acceleration equals F net over mass, which is 1. So that's 1.8 meters per second squared is the acceleration down the ramp. That gives us A. Okay, VF. Going to use the same formula we used before. So this is for A, for VF. We get VF squared. Okay. Equal sign. Okay, so okay, so here we go, 2 times acceleration, what we got here, 20 is the length, so VF squared equals 72. And this gives us 8.5 for VF, meters per second. Okay, now we want to know the time. So we could simply use this. No initial velocity. Do the algebra. We did it already. And that gives us 4.7 seconds. The time for it to go down the ramp. Okay. Okay, so now we're going to analyze with energy and work. Here's the thing. When we had no friction, we could use the formula that the potential energy at the top equaled the kinetic energy at the bottom. But with friction, friction is a non-conservative force. You can't do, this is called conservation of energy. Goes from potential to kinetic, but you still, in the case of this problem, it was 84 joules from the last problem. But you can't do that if you have a friction force. That's a non-conservative force, meaning it comes from the outside. It's as though you stuck your hand in there and slowed the block down from sliding down. That would be non-conservative as well. Well, friction force is non-conservative. So we're going to have to do this with work. So we calculated the work going down, the work down the ramp that the Earth does on the block was equal to the force times the distance. And we came up on the last problem with the force, which was 4.2 newtons. That was sliding down. So that's sliding down. So that's going to be 4.2 newtons. Now, the friction force, the work against it is going to use the friction force, but the same distance because it works on it all the way down. So the work of, I should put friction, which is going to be a negative, equals 1.8. That's the friction force we came up with right there, times the distance. And that's going to equal 36. And of course we're measuring this in, and I put work down the ramp. I didn't finish this. Work down the ramp times the distance, 20 meters. And that's going to give you 84 joules. That's the work down the ramp. It's also the change in energy. Remember, work equals delta E, change in energy. All right, and we got that. So it went from potential energy went from 84 up here to 0 down here. Kinetic energy went from 0 up here to 84 down there. Either way you look at it, that's a change in energy of 84. and that's what work equals. And so we confirm that when we multiplied our force times our distance. Now for friction force, it's the friction force, which is in the negative direction, I'll put a negative sign in there, times the distance, and that gives you negative 36 joules. So if you want to know how much energy you're going to have at the bottom, it's going to be the same as the work is going to be the change in energy. So work overall is going to be 84 minus 36 equals 48 joules. See, we could not compute that using mgh equals 1/2 mv squared. We couldn't because it's not a conservation of energy. You have something interfering with the block going down, the friction force. So we have to use the work method to figure out what the change in energy is. So this is 48 joules equals work, which also equals the change in energy from the top to the bottom. Work is just change. Work and energy are both measured in joules, so they're essentially the same thing. Okay, so that takes care of this problem. Okay, we're on to problem number 3. This is a ramp problem, no friction, but you are going to have an initial velocity up the ramp. This is one that we did in class, so let's go ahead and see this. So free body diagram looks like this. No friction. I'm going to draw our triangle here. Okay, so we'll come down here, draw the component diagram. It'll look something like this. Try to keep it even there. Okay, so this, we don't care about the normal really because there's no friction force, but we do care about this because we need to get the acceleration. Alright, so we're going to come up here. And again, we're assuming that mass equals 1 kilogram. Okay, and it gives us the same acceleration as we had in the very first problem where there was no friction, and that's going to be 4.2 meters per second squared. Okay. So now we're going to just use kinematic formulas. So we're going to have the up part of the problem, and that is where the block starts off, and we're going to push it up the ramp at 5 meters per second. So let's write down what we have. Acceleration, if we're pushing it up, then the acceleration is going to be negative because it's pulling it down. So we're going to call that negative 4.2. The initial velocity is 5 meters per second. That's what it's set up here that we're pushing it up with. We know when it gets to the highest point on the ramp, it's going to come to a stop, so we have a final velocity. And let's go ahead and we want to see two things. How far, we want to know the distance up the ramp it goes, I'll call that d up. And we want to know how much time it takes to get up the ramp. Okay. So what can we figure out? Well, distance equals 1/2 a t squared, but we don't know that. So we can figure out time first if we want. We have VF, V0, and A. So we're going to figure out time over here. And it is okay, you can't eliminate V0 because it's not 0. But I'm going to assume you can do the algebra. If you can't, we're going to subtract VO from both sides and divide by A. So we end up with time equals, and so we're going to get, and it's negative 4.2 for the acceleration. Okay, so what we're going to get when we do that is 5 divided by 4.2, and we get this. Okay, now that we have that, we can use this formula for distance. Off screen a little, that's the formula I'm using. Okay, and when we compute all of this, we get distance equals 3 meters. Okay, all right. Now we go to this was the up part. This was figuring out how long and how it takes it to get to the top and how far it goes before it starts coming back down. So now we're going to do that second part of the problem. That's the down part of the problem. Okay, so here we are. So we got to ask yourself now, we're going to redraw the ramp. How high is the block when it starts to come back down? Well, it started off at, just freehand this here, 20 meters. And we said that it went up 3 more meters before it came to a stop. Right there. So that's going to be a total of 23 meters that it's going to slide down. So now we have a new distance to work with. So let's go ahead and write out what we have. The distance is not 20 meters anymore, it's 23 meters. The acceleration is still 4.2, but we're going to call it positive now because it's going down, the block is moving down, the acceleration is pulling it down, so it's pulling it in the positive direction, in the direction of motion. Okay, and we're going to say the initial velocity, once that block gets to the top here, it stops for a split second, then it starts to go back down. So for the second part of the problem, we're going to say the initial velocity is 0. It came to a stop up here. Just like when we throw a ball up into the air, and we say at the highest point it comes to a stop for a split second, okay? Okay, so now this becomes a fairly basic problem. So what we want to figure out is the time it takes it to get to the bottom. Okay, and the final velocity at the bottom. Okay, so we can use the formula to get final velocity. We know VO, we know A, and we know the distance, so we can use this. Okay, so this equals 193. And we're going to just say that VF is close enough. We're going to say it's 13.9 meters per second. Okay, so this is the final velocity here. Now we're going to get the time. Goes away, no initial velocity going down. We're going to solve for time. And we get 3.3 seconds coming down. Okay, so then the final answer for time is not just 3.3, it's the amount of time we said it took for it to get up to its highest point, 1.2. So total time equals time up plus time down. That equals 4.5 seconds total time. Okay, and that takes care of everything for this problem. Okay, we're on to the last of the ramp problems. This is problem 4, and the only difference is you're now pushing the block down the ramp initially with an initial velocity of 3 meters per second. So everything else was set up, all the forces are the same as they were before. All right, and so what we're going to do is we're going to come over here, and we know VO, and we know the distance is 20 meters. All right, and we need to get the acceleration. So acceleration is going to equal force over mass, and it's the same as it's been for all the other problems. It's mg sine 25 over 1. And that's going to equal 4.5. It has not changed from any of the other problems. 4.2 meters per second squared. Okay, so now we know an acceleration. Okay, so now we're going to go for VF. Okay, so now our VF is 3 from up here, and we got to square that, and that will give us a final velocity. Okay, gives us that. And we get our final velocity of 13.3 meters per second. So we want to know how long it took to go down the ramp. So we'll come over here and do time. Doing the algebra, we get that. Okay, and the time down is 1.98 seconds. Okay. Okay, there's no friction, so we can use conservation of energy here. So we're going to say okay, so to use MGH we have to know the height, and we calculated that in an earlier problem. So let's just take it here as 8.4 meters. So now we're going to solve for VF. Multiply both sides by 2. That cancels there. Divide both sides by M. Those two cancel, and so do those two. So now you have VF squared equals 2GH. Take the square root of both sides, and you get VF equals square root of 2GH. Plug in the numbers. Okay, and finally VF will give us about 13 meters per second. A little bit off from our answer up here. Again, it's always just rounding error when you're off by that much, and it's nothing to worry about. They would not mark you off on the AP exam for that. Okay, this takes care of all the ramp problems. I'll do Atwood machines and other problems on a different video.